Swayam Prabha. Digital India. Educated India.
Alpha greater than 90. I can't help but I have to take some kind of active load, like a motor. Otherwise, we will not be able to really say from the DC side whether we will be able to feed back the power. DC side only resistance, it will not be able to feed back any power. Inductance, it is a passive element. It may store some energy, but it will again not be able to generate anything. So let us take a DC motor drive. Okay. So let us say I have a fully controlled converter. Right? And I am going to have a DC motor drive connected. So according to what alpha I am working at, I will get different values of voltages across the DC motor's armature, because of which I will be able to look at different values of speeds in the DC motor, right? Voltage is essentially going to decide what is the speed, and current is going to decide what is the torque, okay? So torque is proportional to IF IA, and EB is proportional to IF. If I forget about flux, I write in the form of field current IF omega. Okay. So obviously, I can say the voltage is going to decide the speed, and T is going to be decided by the armature current under constant excitation. Fine. Now, I have the three-phase voltages here. A, B, C. Let us say my machine is probably working at alpha equal to 80 degrees. Very large alpha I am working at, maybe alpha equal to 80 degrees I am working. And I have a large armature inductance. So maybe the current is continuous and it is working at certain speed. Maybe I can say 1200 RPM, 1500 RPM, whatever. And it is drawing probably a 5 ampere current, and maybe it is a 220 volts DC motor drive. So I am having not really 220 volts. Currently I am getting less than that because I am working at alpha equal to 80 degrees. Maybe I am going to get much. So this is rated. So maybe I am going to have only say 100, 120 volts, whatever. This is the voltage I am having. Average, everything is average. What I am talking about is average, right? Now let us say this machine is fitted into a vehicle, okay? And it is moving down the gradient. Maybe you are in a hilly region and it is moving down the gradient. If it is moving down the gradient, the speed will automatically increase. Whether you like it or not, the gravity is going to aid it, the speed will increase. If the speed increases, originally it was working at 1200 RPM and back EMF would have been less than 100 volts, maybe back EMF would have been 98 volts, 95 volts, whatever. But now the speed is going from 1200 to 1500 RPM, let us say. It is just going quickly. So, I will have definitely this back EMF, instead of originally whatever was the 95 volts back EMF, now it may become 105 volts or 110 volts because of increase in the speed. So from 1200, let us say the speed has become 1500 RPM. If the speed increases, the back EMF is going to increase. If the back EMF increases from 100 volts, no way I will be able to push the current into 105 volts. No way. I will not be able to really push the current into 105 volts compared to what my 100 volts is. So, I necessarily need to do something and I want to control the speed. So, I might incorporate something called braking in this particular case. So if I want to incorporate braking, or whenever I want to even stop the motor drive or whatever, even when it is moving down the gradient, I might like to stop it eventually at some point, right? So if I have to stop it, in that case, only way I can do it is to feed the power that is being generated in this machine. I'm calling this as a machine now, not motor. I have to feed the power that is generated because of downward movement of the machine, which is working like a kinetic energy generator. So the machine will essentially start generating power. Can I feed it back to the mains? That's what I have to check, right? If I can feed it back to the mains, nothing like it, right? Because I'm not wasting the energy. The downward movement because of gravity is also being converted into electrical energy, and I am feeding it back to the mains. Nothing like it if I can do that. That is being done in Delhi Metro very regularly. Delhi Metro uses regenerative braking most of the times. So if I do that, for that, one thing I need to do is, if this is my field current, I must have had my back EMF somewhat like this, right? And when from this plus, the current was moving to this plus, this was actually working like a load and this was working like a source, right? Now I want this the other way round. And I know for sure that these will conduct current only in this direction. They are set in stone. I can't do anything. So only thing I may be able to do is, if I want to make the power flow direction reverse. I don't want the power to flow from the AC side into DC side. I want the power to flow from the DC side into AC side. Right? I can't reverse the current. Only thing I can reverse is voltage. I would be able to reverse the voltage in this case. So what I can do is to reverse maybe the field current or reverse the armature first. So this will become plus and this will become minus with the same 105 volts, let us say, right? And I got this 100 volts as the voltage when I had a firing angle of 80. I will get the same 100 volts as minus 100 volts if I have a firing angle of hopefully 100 degrees, because 90, if both sides are essentially the same, only thing is one is minus cos alpha, the other one is plus cos alpha. Cos 80 will be equal to magnitude wise cos of 100. Both of them should be equal to each other. So all I need to do is to make this alpha shift from 80 to 100 and also reverse the armature EB. EB reversal can be either done by field current reversal or EB reversal can be done by armature terminal reversal itself. Of course, armature terminal reversal is not a joke because it will be carrying a huge current. You have to disconnect and reconnect. It's not very easy, but it is being done. It is being done in some, not in Delhi Metro. Delhi Metro, this is not being used. It's a little different way of regenerative braking. But in Chennai, in some of the portions, yes, they use it. Old suburban train service where they are still using DC motors, good old DC motors, right? Whereas what we use here, most of them are induction motors, right? So, if I make alpha equal to 100 degrees, now imagine I am going to have plus here and minus here for the VDC after alpha becomes 100 degrees. Now, I have reversed this as well. I have reversed this as well. Now, from here to here, the current will flow. The current direction has not reversed. The voltage has reversed. Because the voltage has reversed and the current direction has not reversed, You are essentially looking at, instead of the AC power being fed to the DC motor drive, we are having the DC generated power from the machine being fed to the three-phase supply. I have only thyristors which can conduct only in one direction. So I can't afford to change the current direction. I cannot change the current direction even if I want to. So only way I can really reverse the power flow is by reversing the voltage. And voltage can be reversed by making alpha greater than 90. And when I make alpha greater than 90, just to make sure that it will be in a position to feed, I have to make this plus and minus of the motor drive also conducive. Otherwise it will not work. That is what is dual converter. Excellent. We will come to that also, definitely. So he is saying that why can't we have another converter in the opposite direction? Complete full converter we have to have in the opposite direction. Yes, absolutely. Only thing, you will be increasing the cost. If you are okay with increasing the cost, yes, by all means. So when we have two such converters, we call it as a dual converter. When we have only one converter, we call that as a two-quadrant converter. This we call as two-quadrant converter because I will be able to have current only in one direction, but voltage can be in both directions. So fully controlled converter is a two-quadrant converter. It will operate in both first and fourth quadrant. This is true only in fully controlled converter. Semi-controlled, very clearly the voltage cannot reverse. We said that already. So if I want regenerative braking, I cannot implement regenerative braking with semi-controlled converter because no way I can reverse the voltage. So power flow can never be in the opposite direction. So although semi-controlled converter gives me a higher voltage, maybe the control is somewhat simpler because only 3 devices have to be controlled. But basically it is not used in some applications where I am looking for regenerated power. Typically electric vehicles, we will never use this kind of, where regeneration cannot happen. Because electric vehicles, especially in the case of vehicles stop and go traffic, you will stop every now and then. And you want to regenerate that power. And you want to maximize the battery going for longer. So we will never use generally semi-controlled converter in any of those applications where we are looking for regeneration. Whereas we will use normally fully controlled converter if we want to save on cost. If you don't mind, spending a little bit more money, we'll go for something called dual converter.
Can we reverse the polarity of the battery? And suppose the net voltage that is being, suppose that we have some armature resistance. So shouldn't the current suddenly want to increase?
When you?
When we change the polarity.
Polarity. Simultaneously you will do this also. You will never do it only one. You have to reverse the polarity of this plus make alpha greater than 90. दोनों इकट्ठा करना पड़ेगा simultaneously. So whatever is the changeover switch which is reversing, his question was, if you only reverse this, by chance you have still not done the alpha greater than 90, then they will become additive, right? It will become like plugging. What you guys have studied in electrical machines, right? Reverse current braking or plugging, where you are going to have essentially the machine basically, looking at huge amount of voltage coming up because its back EMF comes in addition to whatever is the applied voltage. So you will never do that because if you do that, you will be damaging the machine. So you will normally do both simultaneously. So all these things have to be done with time precision. Very clear precision of time. Right? We talked about so far semi-controlled or half-controlled. Semi-controlled is definitely not the same as half-wave. So semi-controlled is only meant for single quadrant. That is, V and I both cannot reverse. Whereas if I talk about fully controlled converter is two quadrant operation is possible because I am going to have V can be reversed, I cannot be. Right? Whereas dual converter, what we are going to discuss now, right? This actually corresponds to all four quadrants of operation. Right? So you can have voltage as well as current both reversed. So we are actually looking at one fully controlled converter here and another fully controlled converter here. Right? And then I'm going to have a three-phase supply. The same three-phase supply will feed this as well. So I can simply draw the three-phase supply and then it is all connected together. I should show it as though this is connected here, this is connected here, and this is connected here. So three-phase supply is the same for both of them, right? One is in the forward direction, the other one is in the reverse direction. So I'm going to have a load connected here. Let me show it as a DC motor. That's it. I have not connected the positive side deliberately. Because if I am trying to fire both the converters simultaneously, right? What I want is this voltage, whatever comes up here, if I call this as VD1 and if I call this as VD2, I want VD1 equal to VD2, average value. If the values are not equal, then if I try to connect them together, I will have a flashover, right? So I have to have VD1 equal to VD2. So I should say VD1 equal to 3 Vm by pi cos alpha, alpha 1. If I may call this as converter 1 and firing angle alpha 1. This is converter 2, firing angle alpha 2. So VD2 has to be actually minus 3 Vm by pi cos alpha 2, because I am just specifying VD2 in the opposite direction. I am not showing this as plus and this is minus. I am rather showing this as plus and this as minus. Right? I am showing that as the voltage rise. So it has to be minus 3 Vm by pi cos alpha 2. These two have to be equal to each other. If I don't want flashover, these two have to be equal to each other, which means cos alpha 1 plus cos alpha 2 equal to 0. This will give me the solution alpha 1 equal to pi minus alpha 2. This will be the solution I will get. So if I am firing one of them at 70 degrees, I should fire the other one at 110 degrees. That's what it means, right? So I have to fire both of them simultaneously but at different firing angles. So if I try to do that, for example, let us say I am firing 1 at alpha equal to 60. We all now have at least, I hope you guys have gotten familiar with this alpha equal to 60 degree waveform. This is alpha equal to 60 degree waveform, normally. Right? If alpha equal to 120, what kind of waveform I have to get? I have to check. Let me draw that also. So alpha 1 is fired at 60 degrees. So alpha 2 has to be 120 degrees. So if I try to draw the waveform corresponding to alpha 2 equal to 120 degrees, let me just draw the three-phase waveform again. The frequencies I have drawn are different, doesn't matter. So I should have drawn with a different color. Right. So these are the three-phase waveforms. So this is A, B, C. Where is alpha equal to 120? This is 30, this is 30, this is 90, this is 120. Right? So this is where I have to fire 1. That means I have to fire 2 here, 3 here, 4 here, and 5 here, and 6 here. Am I right? This is alpha equal to 120. So for alpha equal to 120, if I am firing, here I have to get basically during this portion from here until here, I should be getting 6 and 1 conducting. And from here until here, it will be 1 and 2 and so on. When 6 and 1 are conducting, it is VAB. So let me try to see what is the kind of VAB I am going to have. Here is my A and here is my B. This is A and this is B, right? B is here. B is higher than A, right? B is higher than A because when I am, so this is the kind of voltage I am going to get. This is the voltage I am getting. What I have shown, that is essentially the kind of voltage that I am going to get. I am showing VAB. Between A and B, whatever is enclosed, I am just shading that. That is the voltage I am getting, VAB. But I am having actually A here and B here. So, I am going to have, no, I have done VAC. Ooh. How do I erase this? That is VAC. I can't erase this. Hi. B is here. So, I should have, sorry. Seriously. So this portion, let me probably just, this is lal wala. This is VAB. Sorry. Am I right? This is VAB. What I have shaded originally was VAC. That's what I was wondering, how come I am getting positive voltage? So VAB is negative voltage. B is higher than A. Okay? So this is VAB. So VAB is negative voltage. So I am going to get some voltage like this continuously. Please compare that voltage with this voltage. Average value will be the same because I am inverting this. This is ulta, it is connected ulta because VD2 is connected with positive terminal to the bottom and negative terminal to the top. So exactly ulta connection I am making. So, I will have one of the voltages like this, the other voltage, so I can draw the two voltages. If one of the voltages is like this, right, this is VD1, the other voltage will be somewhat like this. If I try to draw the same thing, I am going to have something like this. This is minus VD2. Or plus VD2, whatever. Okay. So I'm talking about what is the VD2 value and what is the VD1 value. Two converters voltages. Average values will turn out to be the same. This is for alpha equal to 60 and this is for alpha equal to 120. no doubt. But instantaneously the voltages are not the same. Look at the value. This is at minimum, that is at maximum. Here this is at maximum, that is at minimum. So I am not going to have the instantaneous values of voltages of converter 1 and converter 2 to be the same at all. They are different. They are different. So if I try to tie them up directly, there can be a huge current circulating through the two converters. That is the reason why normally I am going to have generally a reactor with a small resistance also. Current limiting reactor. That's what we put. So that di by dt is also minimized. Inductor is always going to minimize di by dt. And the resistance will also minimize the current that is circulating through the entire two converter configuration. Right? So we will look at the dual converter again in the next class, and then we'll go over to the last topic in the AC-DC converter, which will be commutation overlap. That is the last topic, and with that we will conclude on converters, AC-DC rectifier.